Hello, my name is Thaddeus Wagner and my partner is JT Hebron. Today we will be discussing the kinematic equations of constant acceleration. We recorded data on the equation by having 4 different tests with 2 different objects. The first of the 2 tests was done with a basketball that was dropped from 2 different heights. The first height was at the height of 9 feet, the second height was 15 feet. The second set of tests was done with a racquetball. This set of tests were also dropped from the same 2 heights of 15 feet and 9 feet. The 2 balls in question had a large difference in mass, but had the same drop distance. So why is this important? These equations allow us to understand many of the founding mathematical principles of physics and engineering. These equations are what allowed us to understand and calculate the gravitational pull of the Earth. They also allow us to calculate the escape velocity from Earth and many, many more things as well. They are one of the founding blocks of engineering, especially when it has to do with objects in motion.
I'm JT, and this is how the kinematic constant acceleration equations work. The kinematic equation that we used for our research was the equation of velocity squared equals velocity initial squared plus 2 times the constant acceleration times the whole distance minus the original distance. Our given for our basketball is the S naught, which is the starting point, is 0 feet. The delta S is 9 feet. The time that it took for the object to make the entire distance was 0.54 seconds. Velocity naught is 0 because that's when you're holding the object before you drop it. Velocity, the instantaneous velocity of the basketball is determined by taking the distance that it covers in one frame of film and divide that by the time for one specific frame. We determined that it went 9 inches in 0.0167 seconds. This breaks into 539 inches per second, which converts into 45 feet per second. This is determined by multiplying dividing the 539 by 12, because there are 12 inches in 1 foot. Plugging those numbers into our equation, 45 is what we had for our v. So it's 45 squared equals 0 because our v naught was 0. So that's 0 squared plus 2 times our constant acceleration, which is what we are looking for, times our delta s minus our s naught. 45 squared is 2,025, which equals 2 times AC times 9. AC eventually breaks down into 2,025 is equal to 18 AC. Our final constant acceleration for the basketball is 113 feet per second squared. Now, because you're dropping a ball, you must also account for air drag. Air drag is determined by the weight of the object minus the air drag equals the mass of the object times the constant acceleration. Weight breaks down into the mass of the object times gravity minus the air drag equals mass times acceleration. To get air drag, you move the MA over and you move the air drag to the other side, and you get mass times gravity minus mass times constant acceleration equals mass times equals force of the air drag. Now the weight of our ball is 8 pounds. The mass of the ball is determined by taking that 8 pounds and dividing it by the constant acceleration of gravity, which is 32.2 feet per second. That equals 0.25 pounds of mass. Plugging all that back into our equation, we have the 8 pounds, which is the weight of our object, minus the mass of our object, 0.25, times the acceleration that we gathered, 113, equals our air drag. That breaks into 8 minus 21.81. Our air drag ended up being negative 20.1 pounds of force. Now we're going to go over to the racquetball equation, and we're going to do the same thing. The same given. The S naught is still 0 feet because you haven't dropped the object yet. The full length of it which it travels is still 9 feet. The weight, though, of this racquetball, because a basketball is this big and a racquetball is this big, the racquetball weighs 0.1 pounds. Its mass is 0.1 pounds divided by 32.2 feet per second squared, which we get is 0.0031 pounds of mass. The time that it took for the racquetball to travel the entire distance is 0.36 seconds. Its velocity initial is also 0 feet per second because, again, we have not dropped the object. The velocity is determined as in we calculated that it moved 15 inches in 1 frame. The time it takes for 1 frame is still 0.0167 seconds. This division equals 898 inches per second, which is equivalent to 75 feet per second. Now we're going to use the same equation that we used before. V squared equals V naught squared plus 2AC times S minus S naught. If we take our given numbers and we plug them in, it's 75 feet per second squared equals 0 feet per second squared plus 2 times the constant acceleration times the 9, which again breaks down into 5,625 feet per second squared, per second squared, which equals 18 feet times AC. AC ends up being 313 feet per second. Again, we also, because it is a ball, we must calculate for air drag. Air drag is the same equation. Weight minus the force of the air drag equals the mass times acceleration, which breaks down again into mass times gravity minus mass times acceleration equals force of air drag. Plugging our given numbers in, we get 0.1 minus 0.0031 times 313, which is the acceleration that we calculated, equals the force of our air drag. 0.1 minus the product of 0.0031 and 313 is equal to 0.9703, which is equal to the air drag, which we calculate, and we get our air drag is equal to negative 0.87 pounds of force. All right, as you can see, we use the same methods that we used for the 9 feet for when we dropped the two objects at 15 feet. As you can see, same given, S naught, delta S, time, velocity initial, velocity, mass, and weight. All are gathered by doing the same processes that we explained at 9 feet. The equations are the same too. At 15 feet, we also use V squared equals V naught squared plus 2AC times S minus S naught. Plugging in the given in the same manner, we were able to get that the constant acceleration is 118 feet per second squared. Again, air drag is the same thing. Weight minus force of the air drag equals ma, which breaks into mass times gravity minus mass times acceleration equals force times the air equals force of the air drag, which, plugging in our given as we did 9 feet, gives us a negative 391 pounds of force. It's a lot of air drag. The racquetball is again explained the same as we explained at 9 feet. We have S naught, we have delta S, time, velocity initial, velocity, weight, and mass. Plugging them into the equations, we get the same thing, because we also use V squared equals V naught squared plus 2AC times S minus S naught. Plugging in our given, we are able to calculate that the acceleration is 163 feet per second squared. Air drag, again, is the same as it was at 9 feet. Weight minus force of air drag equals ma. Mass times gravity minus mass times acceleration equals force of air drag. By plugging in our given and plugging in the acceleration that we calculated, we get that the force of the air drag is negative 0.405 pounds of force.
Test number 1, basketball. Ready? Go. Number 2, using racquetball. Ready? Go. Test number 2, using the basketball. Well, number 3. Ready? Wait. Ready? Go. Alright. Test number 4, using racquetball. It's focusing, sorry. Alright, ready? Go.
And now go.
Hello, my name is Thaddeus. This is the velocity for the 9-foot drop, what it should be. This is what the velocity should be for the 15-foot drop. The proper acceleration is 32.3 feet per second squared. The reason why we didn't get that was a number of reasons. First off is human error with the videotaping and whatnot, and the glare that happened on the tape measure. And the other reason why is because of air drag, which occurred naturally because the ball was falling through space with air.
All right, you're good. Do it the square.